Number 8 from the worksheet. So this questions is the most difficult homework problem of the homework 1 here. So make sure that you totally understand the concept of strong base, strong acid, weak base, and weak acid, and the buffer questions before doing these problems. So number 8 is it asks you to calculation the compositions of two buffer, which compose of the same component, which is ethanolamine and acetic acid. And it also asks you which one of these buffer will be a better buffer. So in other words, it's have which one will have the greater buffering capacity. So one thing to notice is that these buffer, they compose of the same chemicals here, which are ethanolamine and acetic acid. But the difference is they are at different pH, right? And so the question asks you which one will be the better buffer than the another. So please go back and review the property of the good buffer. What is the definition of the good buffer? So the first one is the good buffer need to have higher concentration or maybe higher volume, higher amount of mole, because the higher the concentration it is, the better, the greater buffering capacity that it can neutralize the acid or neutralize the base that is being formed from the reaction. And the second reason, the second property of the good buffer is that it should not interfere with normal biochemical reaction in the body, because if it's interfered, it would be change or affect the biochemical process of our body system. Come back to the compositions of our buffer here. So ethanolamine, when you mix it with the acetic acid, it will change to ethanolamonium and acetate. So you can notice here that we have two different buffer systems. Here, the first one is the pairs of ethanolamine and ethanolamonium, while the second one is the pairs of acetic acid and acetate. Well, in this case, how do this work? So you notice that the two buffer that we have here, the pH are different, right? So because we have the pKa of ethanolamine equal 9.44, whereas pKa of acetic acid is just only 4.76. So one buffer system would work only one system at a certain pH. Okay, so because the first one we have the pH equal 5, since pH equal 5 is the closer to pKa of acetic acid, 4.76 here. So it means that at pH 5, the pairs of acetic acid and acetate will work as a buffer system. Compared to the buffer at pH 9.2, because it's close to the pKa of ethanolamine, so at pH 9.2, the pairs of ethanolamine and ethanolamonium will work as the buffer. Starting at pH 5, the buffer at pH 5, let's see what happened in the buffer at pH 5. So we know that at pH 5, the buffer system would fall to the acetic and acetate. And initially, we only have ethanolamine and acetic acid. So to make the acetate here, it has to be changed from ethanolamine, because ethanolamine will react with acetic acid and then it's changed to ethanol, ammonium, and acetate. So if at pH 5, there's are only acetic acid and acetate, it means that in the way how ethanolamine react with acetic at equilibrium, it has to be no ethanolamine left over, because any ethanolamine that left over will still react with acetic acid and will be changed to acetate, and then that change amount would alter the ratio at pH 5, and thus the pH would not remain 5. So the ratio of acetic and acetate at pH 5 can be calculated using the Henderson-Hasselbalch equation, and so for A and B ratio here. Henderson-Hasselbalch equation, you plug in 5 as a pH and then use 4.76 as the pKa, because right now we're talking about acetic and acetate. So we use 4.76, then plus log B over A. A would equal 0.365, while B equal 0.635. So at this point, you can see that we can plug these two values back into the ice table over here. One thing to notice from the question is that it doesn't say the concentration of each of the acetic acid in these two different buffers. Well, it's because that we have to find the concentration of the initial concentration of acetic acid in order to know which one, in order to determine which one will be a good buffer. So, okay, come back to the ice table over here. We calculate from the Henderson-Hasselbalch equation, and we got the equivalent, the equilibrium equivalence of either the acetic acid and the acetate will be this value. So to calculate the concentration of initial acetic acid in the buffer, you have to work backward. By that, I mean you have to think about the change amount lie here. So because at equilibrium, you would have 0.635 acetate, and for sure, we don't have any acetate at the initial condition. So it means that the amount that had been changed for acetate is actually 0.635, and this amount is applied to every chemicals here. Acetic acid also changed by 0.635, and ethanolamine actually changed for 0.635. So the three lines over here, I put equivalence because every value in these three lines would be the equivalence, not the concentration, not the mole. Only line that I put the concentration is the first line here when we will use it as the final calculations. Okay, so as we can see here that the change amount of each chemical would be 0.635, and we know that at equilibrium, ethanolamine would become 0. So because now you can work backward to the initial line of equivalence at this step here. So because at equilibrium, ethanolamine will be all neutralized out of the system, it means that initial equivalence of ethanolamine would equal 0.635. Following me so far? So that's why when it change, it becomes zero at equilibrium, right? And for acetic acid, you between the chain line and equilibrium line here, you can also work backward and then get the initial equivalence of acetic acid as 1, right? So 1 minus 0.635, so that's why you have the equivalence of acetic acid at equilibrium equal 0.365. Therefore, to calculate the initial concentration of acetic acid, you would use this information over here to calculate. So we know that ethanolamine equivalence at initial would be 0.635 and equivalence of acetic acid at initial would be 1. So we can say that 0.635 equivalence equal to 0.1 molar. So because we start, from the equations, it starts with ethanolamine 0.1 molar, and then at equilibrium, we have to take all of ethanolamine out of the system. And so we know that initial equivalence of ethanolamine is 0.635. So we can say that 0.635 equivalence would equal 0.1 molar. And then for the concentration of acetic acid, we know that it's begin with 1 equivalent, right, from the ice table here. So we can calculate by comparing back to the amount of ethanolamine that you have initially, and so 1 equivalence would be equal 0.1 divided by 0.635 here, and this would equal 0.157 molar. So now we already solved that the concentration of acetic acid that needs to be mixed with 0.1 molar ethanolamine is equal 0.157 molar. And this is the initial concentration of acetic acid. And I will write it back here. So it's 0.157 molar. So again, when you have 0.1 molar ethanolamine mixed with 0.157 molar of acetic acid, the reaction of the buffer will explain by this ice table. So 0.1 molar of ethanolamine will be taken out of the system by react with the acetic acid here. Okay, I hope you're following me so far. This is kind of complicated and confusing, but bear with it. So in summary, for the buffer 1, the first buffer, the initial concentration of acetic acid is 0.157 molar. And then for the second buffer here, you still need to calculate the initial concentration of acetic acid. And since we say that at pH 5, the pairs of the buffer that work is acetic acid. So this amount of initial concentration of acetic acid will be taken into consideration. While at pH 9.2, the pairs of buffer that work will be the 0.1 molar of ethanolamine. Actually, at this point, you can see and you can choose which one is the better buffer, because since we say that at pH 5, the one that work would be the acetic acid. So the concentration or the molarity of acetic acid is 0.157 molar. But at pH 9.2, the one that will work will be the part of ethanolamine. And since we only have 0.1 molar of ethanolamine, so at this point you can say that, well, the buffer number one here might be better because the concentration of the buffer system, acetic acid in this case, is higher and higher concentration than the 0.1 ethanolamine of the second buffer. So then what happened at pH 9.2? So 9.2, the ethanolamine will work as a buffer. So at equilibrium, you have to neutralize all of acetic acid out of the system. Okay, so to fill in the ice table of the equilibrium line, you still need to use the Henderson-Hasselbalch equation. So pH equal pKa plus log B over A again. So pH would be 9.2. The pKa in this case need to be the pKa of ethanolamine. It's 9.44. And then you calculate for the ratio B and A. So the A ratio, you get 0.64 equivalents, and B, you get 0.36 equivalent. So this value here, you can plug in into the ice table. And now you have to work backward again to solve for the change line and then the initial line, right? So since we begin with ethanolamine, 0 of ethanolamine, not ethanol, we begin with 0 of ethanol ammonium. So it means that the amount that had been formed is actually all of the amount that has been changed, right? So this 0.64 here would apply to every chemical because the reaction, there's only 1-to-1 equivalence of across the reaction here. So for the initial equivalence line, you would see that we begin with 1 equivalence of ethanolamine, but 0.64 equivalent of acetic acid, right? Because we have to neutralize all of the acetic acid out of the system. So now you can say that since we have 1 equivalence of ethanolamine at the initial concentration, 1 equivalence would be equal 0.1 molar. That is what you are given, right? But since we want to know the concentration of the acetic acid here, so we can say that if 1 equivalence equal 0.1 molar, we want to know 0.64 equivalence because we start from 0.64 equivalence of acetic acid. What will be the concentration of 0.64 equivalence? So to solve for this, 0.64 equivalence would equal 0.1 divided by 1 and then times by 0.64, right? And this would equal 0.064 molar. So the of the acetic acid at the initial state equal 0.064 molar. So now we got the answer for these questions. So to calculate the compositions of two buffer, we have already calculated the concentration of acetic acid in each of these two buffer. Is different because these two buffer give you the different pH. So the ratio of either ethanolamine, ethanolamonium acetic or acetate would fall into the Henderson-Hasselbalch equation and fall in the right ratio, right? So which one have the greater buffering capacity? We already talked that you have to focus on the buffer that work at that certain pH. So at pH 5, the one that work as a buffer would be acetic acid. And the concentration of acetic acid in the system is 0.157 molar. Comparing to the buffer at pH 9.2, the one that work at the buffer will be 0.1 ethanolamines. And you know that it's just 0.1 molar ethanolamine. So to compare which one is the greater buffer, so we say that the better buffer would have higher morality. So this would be the answer. The buffer, the first buffer here will be the better buffer than the second one because it's just have higher morality of acetic acid than the concentration of ethanolamine in the second buffer. So I know that this question is very confused, some of you. So I'm more than happy to answer questions. If you still stuck on it, you can send me an email or leave me message anytime. I will get back to you as soon as possible. Thank you.